Hocam.
Kayıt başladı şu anda. The recording is started now. So this is nanotechnology and nanosensor class, 31st March. It's online class, and AFM Azizi is presenting his first presentation on atomic force microscopy. Go ahead, Ehsan.
Good afternoon. My name is AFM Azizi, and the topic of my presentation is atomic force microscopy. This is the outline of my presentation. I will go through the history and then the characteristics of this microscopy, then the working principles, mode of operation, applications, and finally the advantages and disadvantages. First, the history. In the early 1980s, Gerd Bennig and Heinrich Rohrer described scanning tunneling microscope. Then Benning invented the atomic force microscopy, and the first experimental implementation was made in 1986. But to commercialize it, it took some time, and the first commercially available atomic force microscope was introduced in 1989. The atomic force microscope is one of the foremost tools for imaging, measuring, and manipulating matter at nanoscale. Characteristics of atomic force microscope. It demonstrates resolution on the order of fractions of a nanometer, more than 1,000 times better than the optical diffraction limit. There's no need of focusing, illumination, depth of field, and unlike a scanning tunneling microscope, samples do not need to be conductive. And unlike other types of electron microscopes such as SEM and TEM, samples do not need to be coated or stained, thus minimal damage and easy sample preparation is available with this type of microscope. It also have height information that makes it possible to quickly measure the height, volume, width, and of any feature in the sample. It physically feeds the sample surface with a sharp probe, building up a map of the height of the sample surfaces. It provides single atomic level structures, so the resolution is quite high. This is a comparative table that compares the atomic force microscopy to other types of microscopies such as scanning tunneling microscopy, SEM, and TEM. In here, we see that the biggest advantage, the biggest positive points of atomic force microscopy, as we can see here, the environment, the STM, TEM, and SEM, they require vacuum and air, but AFM can operate in every environment. And also it provides a 3D, three-dimensional imaging system when compared to TEM and SEM. And samples can be anything, but in this, in case of other ones, they should be conductors or semiconductors, and so on. The working principle. The atomic force microscopy principle is based on the cantilever assembly that interacts with the sample. This assembly is also commonly referred to as the probe. The atomic force microscope probe interacts with the substrate through a raster scanning motion. The up-down and side-to-side motion of the atomic force microscope tip as it scans along the surface is monitored through a laser beam reflected on the cantilever. This reflected laser beam is tracked by a position-sensitive photodetector called the PSPD that picks up the vertical and lateral motion of the probe. The deflection sensitivity of these detectors has to be calibrated in terms of how many nanometers of motion correspond to a unit of voltage measured on the detector. But in order to achieve the atomic force microscope modes known as the tapping modes, the probe is mounted into a holder with a shaker piezo in here, as is shown. And the shaker piezo provides the ability to oscillate the probe at a wide range of frequencies, but the typical frequency is between 100 hertz to 2 megahertz. Modes of operation. This microscope basically has three modes of operation: contact, non-contact, and tapping mode. The first one is contact mode. In contact mode, the resolution is high. Tip of the probe always is touching the sample. It has the fastest of all topographic modes. Because of the repulsive forces, tip and sample may damage because it's constantly into contact with the sample, and it's sensitive to the nature of the sample, but it's not good for soft samples. It has some advantages: fast scanning, good for rough samples, used in friction analysis. But the main disadvantage is the force may damage or deform soft samples. The second mode of operation is non-contact mode. It's also known as dynamic force microscope. Tip is oscillated near its resonant frequency without touching the surface. Signal-to-noise benefits associated with the modulated signals. Oscillating modes can measure images with a small probe sample force. The advantages of this mode of operation is it has very low force exerted on the sample, between 10 to 12 Newton. Extended probe, and it has an extended probe lifetime since it's not in contact with the sample, so it's not eroded. Used in fragile biological samples like protein and DNA. It has some disadvantages. The resolution is low because it's not in contact with the sample, and it cannot be get the exact topography of the sample. Containment layer on surface can interfere with oscillation. Usually need ultra high vacuum to have best imaging, but it's difficult in practice. The third mode of operation is called the tapping mode. It's 0.5 to 2 nanometers probe surface separation. The distance between the probe and the sample should be between 0.5 to 2 nanometers. Tip is oscillated at its resonance frequency. Tip vibrates at 105 hertz, close to specimen surface with amplitude 10 to 100 nanometer. Is used for imaging in air. The advantage is high resolution of samples that are easily damaged, and it's good for biological samples. Applications. The AFM has been applied to problems in a wide range of disciplines of the natural sciences, including solid-state physics, semiconductor science and technology, molecular engineering, polymer chemistry and physics, surface chemistry, molecular biology, and cell biology. For example, in the field of solid-state physics includes the identification of atoms at the surface, the evaluation of interaction between a specific atom and its neighboring atoms, and the study of changes in physical properties arising from changes in atomic arrangement through atomic manipulation. Of the many in molecular biology, atomic force microscope can be used to study the structure and mechanism properties of protein complexes and assemblies. For example, AFM has been used to image microtubules and measure their stiffness. After many SPMs, atomic force microscopy is being used most for biomedical researches, such as unfolding of proteins, imaging of biomolecules, force measurements in real solvent environments, antibody antigen binding studies, ligand receptor binding studies, binding forces of complementary DNA strands, and study surface frictional forces, ion channel localization in the field of biomedical engineering. Atomic and the advantages of this system of image microscopy. AFM has several advantages over the scanning electron microscope, also known as SEM. Unlike the microscope, electron microscope, which provides a two-dimensional projection or two-dimensional image of a sample, the AFM provides a three-dimensional surface profile. In addition, samples viewed by AFM do not require any special treatments such as metal carbon coatings that would irreversibly change or damage the sample, and does not typically suffer from changing artifacts in the final image. While an electron microscope needs an expensive vacuum environment for proper operation, most AFM modes can work perfectly well in ambient air or even in a liquid environment. This makes it possible to study biological macromolecules and even living organisms. In principle, AFM can provide higher resolution than uh, scanning electron microscopy and other types of electron microscopies. The disadvantages of this system. A disadvantage of AFM compared to the scanning electron microscopy in the single scan is the single scan image size. The scanning electron microscope can image an area on the order of square millimeters with a depth of field on the order of millimeters, whereas the AFM can only image a maximum scanning area of about 150 and 150 micrometers and a maximum height on the order of 10 to 20 micrometers. And due to the nature of atomic force microscope probes, they cannot normally measure steep walls or overhangs. These are some examples of atomic force microscope that has been used in different areas, as you can see in nanomechanical analysis of alginate hydrogels, phase image of SPS, PS polymer blend, and cell-cell adhesion, and other examples. Thank you for your attention.
Evet İhsan, teşekkürler.
Ben teşekkür ederim.
Sorusu olan var mı arkadaşlar? Soru sormak isteyenler. Bu örneklerde şeyi
Yine paylaştım hocam.
tekrar paylaşıma getirebilir misin? Örneklerde bir şey soracaktım.
Hocam.
Ya da neyse getirmedi. Şeyde bu yumuşak doku örneklerinde bunlarda AFM kullanılıyor mu yoksa nasıl oluyor?
Hocam AFM kullanılıyor. Çünkü işte bu şeylerde mesela non-contact modu kullanarak ya da tapping modu kullanarak onu hiç dokunmadan şey yapabiliriz onu. Görüntüleme falan yapabiliriz. O yüzden biyolojik alanlarda da kullanılabilir.
Tamam, biosensing öyle o şekilde yapılıyor.
Evet.
Tamam. Oldu. Teşekkürler. Şimdi
Şimdi ikinci sunumum